Welcome back. Today we are going to talk about solutions, or at least we are going to begin our discussion on solutions. Now, before we jump in, let's have a quick overview of what we're going to be talking about in this chapter. Understand that a solution is anything when we have, just a mixture of substances together, whether those substances being a liquid and a solid mixed together, or a liquid and a liquid, or sometimes even liquids and gases. We're going to be exploring all those different types of solutions and lots of different properties of those solutions. So that's one of the things we're going to be talking about, like defining a solution. We're also going to be talking about something called the solution process, how to make solutions, how can we calculate things from solutions, and things like that. And we're also going to be talking about something called solubility, meaning how well do things dissolve in solution. We're also going to be talking about solutions and their physical changes, which we give a very fancy name called colligative properties. These colligative properties are things like boiling point, freezing point, vapor pressure, and another one that's called osmotic pressure. Let's go ahead and jump right into it. So let's start talking about what a solution actually is. A solution is a homogeneous mixture. I've also heard the term homogeneous. I say homogeneous. It doesn't matter. Remember that we've seen this term homogeneous in the past. Homogeneous just means a mixture of things that are uniform throughout. Like you can't see the bits and pieces in a homogeneous mixture. It's nice and uniform, meaning the same. We have lots of different types of solutions. So if you go in the book, they talk about different types of solutions. There are lots of different ways that we can make solutions. Sometimes in our brain, we think about solutions just as like taking a soluble solid and dissolving it in a liquid, and then that's a solution. But there's a lot of different other types of solutions. I mean, you can have gas and liquid, which is a solution. You can have liquids and other liquids, which is a solution. Heck, you can even have like gases and solids. You can even have gases and gases. You can have, there's lots of different solutions. A solution is just anything that is homogeneously mixed together. Now, when we're talking about this chapter, what I've noticed in the past is that something that a lot of students struggle with when we're trying to do this chapter is they get kind of all gunked up in the vocab that we have to use for this chapter. There's a lot of new terminology that we have to use. So I want you to make sure that you pay particular care in learning how to speak the language that we have to talk about in order to understand solubility, and specifically solutions. The first one here is a term called a solvent. The solvent is the substance that does the dissolving. So when we're talking about forming a solution, we have to talk about dissolving something into solution. The solvent is the thing that does the dissolving. The solute is the thing being dissolved. So the solute is dissolved by the solvent. The way that I like to think of it is think about water and salt. If I have salt in my hand and I put it in water and I stir, well, the water dissolves the salt. So the salt is the solute, the water is the solvent. It's as simple as that. Now, most of the time, for the purpose of our course, we're going to be dealing with solutions that are going to be dissolved in water, which means that the solvent is going to be water, which we call these things aqueous or aqueous, depending on what class you're in. I like to say aqueous, but I could see the argument for aqueous. Anyway, most of the time things are going to be aqueous for us, so that means that they're going to be dissolved in water. Water is the solvent. I'm going to try and use that vocab a little bit more so you can keep up with me. And again, we've talked about solubility. We just talked about it previously, but solubility can also be defined as a measure of the degree that a substance can dissolve. It's actually like the amount per gram that can dissolve in a certain amount of solvent, sometimes specifically water. But we'll get more into solubility a little bit later. Let's talk about what's really important to just understand as we get into this is the idea of concentration. So we've talked about concentration before. Remember, we've represented concentration with this unit, molarity. Now, there's a little bit of typo in your notes, so please cross out the word molarity and replace it with concentration. That's why I bolded that there. The concentration of a solution is usually expressed in molarity, which remember is big M. Has to be big M. If you use a little m for molarity, it's not going to work out because later we're going to use little m for something else. So we need to use big M for molarity. Now remember that we can quantify molarity with numerical values. Oftentimes, molarity is moles of the solute, meaning it's the moles of the thing being dissolved, divided by the liters of the solvent, meaning the thing doing the dissolving. Most of the time, in simpler terms, we just write molarity as moles over liters. But it's important to understand what those moles are and what those liters are. So this should be review. Let's look at number 2. Calculate the molarity of a solution prepared by dissolving 125 grams of magnesium chloride in enough water to make 1.23 liters of solution. Because this is review, I'd like you to take some time and try this out on your own. Remember, just try and figure out moles. I can't write moles apparently. Moles over liters. Start there. Calculate your concentration or your molarity. They're the same thing. Come on back when you're done. Hopefully this is what you got. Now, you could have just as well have gotten yourself into moles in a second step and then plugged the moles into the equation to kind of do it in 2 steps. I just did it all at once. Notice on the top I was given grams first, and I can't plug grams into the equation. So I have to take grams and I have to convert them into moles using the molar mass of magnesium chloride. And then I divide those moles by liters and I get concentration. So that's what I get. Now, let's keep going. How about another problem where we are now dealing with, gotta turn my own page, 50 grams of potassium nitrate dissolved in enough water to make 555 milliliters of solution. We're calculating molarity again. Try this one again. If you didn't really get the other one, make sure you correct your mistakes this time. This problem is going to be practically identical. Correct your mistakes, try it again, give this a shot, come on back when you're done. One little mistake that I might predict you may have made, if you made one, was that you might have thought, oh, I could just plug the 555 milliliters into the equation. But remember that that's liters, moles per liter. It's really specific and it has to be that way. So we have to take those 555 milliliters. Those are not the right units for us. Convert them into liters. We also have to convert our grams into moles. And again, the process is very much the same after that. One more. How many grams of potassium sulfate would be dissolved in 12 liters of a 0.0030 molar solution? Okay, so this time concentration is given to us, and we're looking for grams. So I'd like you to pause this one and give this a try. I want you to think about the equation for molarity, and I want you to think about a way that you can manipulate that equation to get yourself into grams. Give it a try. Come on back when you're done. Now notice the first thing that I did was I manipulated my molarity equation to be moles equal concentration times liters. So then if I multiply concentration times liters, I do in fact get moles. Because if you think about it, concentration is just moles over liters, and the liters are going to cancel. So then the thing I'm left with is moles. Moles are going to cancel on the bottom, and the thing I'm left with is grams of K2SO4, which I forgot to write, but you write it. I don't have enough space. So this is a really important relationship to remember, that we can manipulate this equation to be moles equal concentration times liters. It's really useful for us. In fact, we're going to use it right now in something called dilutions. So dilutions is something that what I, as a chemist and your teacher, probably do the most, like in my day-to-day life, when I'm putting together solutions of things for you in labs and creating different solutions that we use in our class. I have to do dilution equations all the time because I don't want to always bring out stuff that's really concentrated or somewhat dangerous for you to use in the lab. So I have to use dilutions. This is how a dilution works. The mole of the solute before you dilute equals the mole of the solute after you dilute. So that means that the moles before we dilute equal the moles after we dilute. Now dilution, the whole concept of this is that maybe we have a solution that is too concentrated, it's too strong, and we don't want to use that concentrated solution. So instead we dilute it and we add water to it in order to cut down on its concentration. This is something that I think everyone can relate to. Maybe if you think back onto when you were a kid, or heck, maybe you do it now. Maybe you're at home and you're making some sort of powdered drink. You know when you talk about you have to scoop out the stuff and pour it into the water. Maybe you're making Kool-Aid or lemonade or energy drinks or whatever it is that you're making. You've probably experienced this sometime in your life where if you have a bunch of water and you scoop in a bunch of powder, and maybe when you were a little kid you were like, oh yeah, it's really good if I put a bunch of powder in there. So you put like way too much powder and you stir it up and then you drink that thing and it tastes awful. It's way too sweet. You know, you can't even drink it. So how did you fix it? Well, you probably poured some of it out and then you added more water to it. This is all a dilution is. I do the same thing in chemistry, except I'm not drinking Kool-Aid in the back. I'm making chemicals, but I just dilute them using water. So we have to make the moles of the solution before dilution also equal the moles of the solution after dilution. So the formula that we use for this is what we call the dilution equation. So M1V1, which if you might recognize, M times V is just moles. We just proved that in the previous problem. So M1V1 equals M2V2, meaning the moles before we dilute equal the moles after we dilute. And there's a really important relationship to think about here. I want you to think about it on your own maybe and see if you can come up with it. But consider the relationship between M1 and M2. I want you to think about it for a second. If I have the concentration in the first and I'm diluting it with water to make a new concentration after dilution, what should happen to the concentration? Should M1 be greater than M2, or should M2 be greater than M1? Think about it for a sec. Maybe pause and think what you would think this would be. Well, hopefully you realize that M1 should be a value that's greater than M2. The first concentration should be higher than the second. I'm diluting the first concentration to give me a second concentration. So it makes sense for it to be less after dilution. Think about that relationship between V1 and V2. V1 is the volume of the solution before we dilute it, and V2 is the volume of the solution after it's been diluted. So what should happen to the volume? Should V1 be greater than V2? Should V2 be greater than V1? Think about it again. It should be greater, right? V1 should be less than V2 because we're adding water to it. It's just something to keep in mind, because a lot of times the only tricky part about these problems is that people just get themselves backwards, and you don't really have to. Just make sure that your numbers make sense. Another way that we can write this equation just for your own information is, instead of writing molarity, we can just write C, where C sometimes just means concentration. And this is just kind of a more general version, because there are other ways that we can calculate concentration, but for the most part, we're dealing in molarity. Just keep that in mind. Let's do a little practice. Calculate the molarity of 100 milliliters of 2.37 molar solution after 50 milliliters of water were added to the solution. So let's think about what we have. You know, let's kind of take stock here. I'm gonna write my letters out. V2 like this. And let's take stock what we have, because this is the equation that we're going to use, right? We're dealing with a dilution. Now it says that I have the molarity. We have a molarity of a 100 milliliter solution. And you might be thinking to yourself like, whoa, that's got to be, what are you doing? That's got to be in liters. Well, dilution problems, they don't really have to be in liters because it's about the ratio between the two. And it's really not going to change anything. So you can keep it in milliliters, but if it makes you uncomfortable, you can put it in liters. It's not a big deal. Anyway, that's the starting volume. And it says our starting concentration is 2.37. Now, it says that we're looking for the molarity, so that means we're probably looking for M2. And would we say that 50 milliliters is V2? Does that make sense? Didn't we just talk about before that V2 should be greater than V1? No, that doesn't make sense, right? 50 milliliters is the amount of water added to the solution. So then what is V2? Maybe we can go up and we can add something more to our little notes here. V2 is actually V1 plus whatever water we're adding. So that means that we would take the water that's being added to this solution and we would add it to our starting milliliters. Hopefully that makes sense, because that's the volume after we're done. We didn't take any water out, we're putting water in. It's just important to keep that in mind. So now we can manipulate this equation to look like this. where we are solving for M2 specifically, and then we just plug in everything that we have. So go ahead and plug them in, calculate this on your own, and then come on back when you're done to just double check your calculator. Okay, this is what I got. If you don't believe me about the whole liters thing, you are welcome to convert these into liters and do the same thing, and you'll notice that you get the same concentration. Again, it's because we're taking the ratio between the volumes, which is why it doesn't really matter if we're in milliliters or liters, but do what makes you comfortable. That's what you get. You get 1.58 molar as far as our concentration. Let's try another one. How many milliliters of water would need to be added, almost read that wrong, to 250 milliliters of a 300 molar solution, I don't know what low is, to make the solution 2.25 molar. So now we are actually looking for the amount of water that's supposed to be added. Okay, so this time we're probably looking for V2, right? So we're going to probably manipulate our equation a little bit, and we're going to look for V2. Go ahead and take a second and continue to practice. Calculate V2, and then come on back when you're done because there's probably a little more that you might not realize that we have to do. Now, if you calculate V2, this is what you should get, right? 333 milliliters. But does that answer the question? The question said how many milliliters of water would need to be added. What we calculated right now with V2 was the amount of water after, or the amount of solution after water was added. So we haven't really answered the question, have we? Remember what we talked about before when we said that V2 equals V1 plus the water that was added? So we need to take the V1 or the V2 that we calculated, and we need to calculate the water that was added. So that means we're looking for this instead. It's just a little bit of algebra. Really, we're just subtracting. So it's just 333 minus 250, and that's going to give us our actual answer, which is 83 milliliters of water added. All right, and that's it. So let's continue on. Let's talk about the solution process. So this is just, again, talking about how things dissolve into solution. When we have an ionic solute dissolved in water, those ions are going to dissociate. Each ion is surrounded by the oppositely charged ends of a water molecule, if that solution is aqueous, meaning that if water is doing the dissolving. And those water molecules actually tear things apart. It's pretty crazy. They surround the ions and they tear them apart. But remember that this isn't a chemical reaction. It's just kind of a temporary state. Because after they get out of the water, they get put back together. But this is called, excuse me, that's not the right word. That says solution. This should be solvation. Not solution, but solvation. I must have just done a little typo there. But it's also called hydration if we're talking about something in water. So let's actually look at this. We have a little bit of a science simulation that we can experience here together to kind of give you an idea of what it looks like. All right, so here we are in the lab. Let's take some salt here. We got to shake the salt out. And, well, we got to make it go. And stop here. So we're dealing with sodium and we're dealing with chlorine. Sodium is kind of the little pink dots. Chlorine is the little green dots. And they are about to fall into water. So let's observe to see what happens when the sodium chloride falls into the water. Okay, go. Oh, see? Oh, look at that. Now notice how the sodium ions and the chlorine ions have separated from the water. Let's do a little shake. Let's get some more in there. Aha, see how they separate. So those things are now dissociated in solution. And if you were to look to, maybe see if you can figure out how many are in there. Let's see. Let's see if we can count real quick. 1, 2, 3, 4, 5, 6. So I got about 74 sodium. And 1, 2, 3, 4, 5, 6, so 74 chlorine. Notice that it's a 1-to-1. That's pretty important to remember, that it's a 1-to-1 ratio between sodium and chlorine dissolved in solution. We'll revisit that in a second. Let's head back to the notes. We have a solution, just like we saw before, that is free-flowing or has movement in solution, and it forms ions. We call those things electrolytic solutions because they have the ability to conduct electricity. Those ions in solution, specifically water, are going to be able to have energy pass through them in the form of electricity. That causes an electric current to pass through, makes it electrolytic. Now, in order to understand that whether or not something's going to dissolve in solution, we have to be able to understand our solubility rules. They're really important. I know that you probably are like, oh, I don't remember my solubility rules. It's time to remember them. Because if something doesn't dissolve in water, then it won't dissociate and it's not going to be able to create a solution. So we need to know what makes a solution and what doesn't make a solution. So make sure you polish up on your solubility rules. Let's do a little practice with this concept. We're going to write dissociation equations. I don't know if you remember what a dissociation equation is, but we're going to try and write the dissociation equation between the three different things that we talked about in part D. So those first examples that we did where we were determining the concentration of things, we are going to write the dissociation equation for each one. I'm going to show you the first one to kind of refresh your memory on how this works, and then I'm going to let you do the next two on your own. So remember that a dissociation equation means that we are taking a solid, a soluble solid, and we are breaking it apart into its ions. This is magnesium chloride. The first thing you do is you write what they are as ions. Magnesium forms a +2 ion, chlorine forms a -1 ion. All ions are aqueous, and then our last little step is that we have to make sure that it's balanced. It's as easy as that. Why don't you try out potassium nitrate and potassium sulfate and see how they go. Come on back when you're done. Hopefully this is what you got. Now, notice that we have a different ratio in moles compared to the things that are being dissolved. For example, if we look at MgCl2, notice that I have 1 mole of magnesium ions dissolving for every 2 moles of chlorine ions. Is that something that actually occurs? Well, let's go back to our simulation and see if we can explore it in the lab. Here we are back in the lab. So now we have a new salt that's very similar to what we had before, where we have MgCl2. We're going to shake. Hold on, before we go. Remember, we're dealing with MgCl2, so we have, hopefully, we're trying to look to see if we have a ratio of a 1:2 ratio between the number of dissolved ions. Let's see. Okay, they're dissolving. All right, so it looks like the black dots are the magnesium and the white dots are the chlorine. And even just by looking, you can see that there's a lot more white dots than there are black dots. Let's see if we can count specifically. So, so I have about 28 cations and about like 66 anions, right? So yeah, it really does show that 1:2 ratio, that there are almost double the amount of chlorines in solution than there are magnesiums. An important thing to keep in mind. Let's head on back to the notes and then let's finish this up. So let's take this through a little bit of practice. Let's draw a picture of magnesium chloride in solution. Let's kind of recreate what we just saw in the lab. So if we have some water here, and inside that water we have magnesium, and I'm just going to do like 6 of those, then we should also understand that we have double the amount of chlorine. So I just drew like 12 of those. So those are the Cl minus, and these are the Mg+2s. So it's important to keep in mind that there's just twice as many chlorines in solution as there are magnesiums. Now let's see if we can calculate the concentration of each ion from the first example. So we're talking about calculating the concentration specifically of the magnesium ion and the chlorine ion from the calculations that we found before. So we're talking about using this dissociation equation to figure out the concentration of each individual ion. Now it sounds kind of tricky, but it's actually not as tricky as you think. And I think that we're going to be able to handle it pretty well. So we have MgCl2 gives us Mg+2 and Cl-. We already know from our previous work that MgCl2 has a concentration of 107 molar. So can we calculate the concentration of the other 2 ions? Well, this is just stoichiometry, really. We're going to take 107 molar, which is the concentration of MgCl2, and we can use the balanced chemical equation I have 1 ion of MgCl2 for every 1 Mg plus 2, and that gives me the same concentration of 107. But if I were to do this with Cl2, or excuse me, Cl minus, you will notice that something interesting happens to my concentration. In fact, my concentration doubles. This was for Mg plus. Very interesting, just as we have observed. Calculate the concentration of each ion in the second example of part D in the notes. So now we are dealing with KNO3. So we are dealing with the concentration of KNO3, which is 0.892 molar. Give this one a try. Try it out. I'm not exactly showing all the work, but I would really hope that you would show all the work. Again, we are just going to go from the concentration of KNO3, and using the balanced dissociation equation that we already wrote, we can find out the concentration of each individual ion. Can we do it for our last one, which is K2SO4, which has a concentration of 0.3 molar? I think we can. Give it a try and come back when you're done. Hopefully this is what you got. Again, make sure that you show the work so you understand what you're doing when you go back and look at it again, but that's all it takes. We can easily calculate the concentration of the ions just by looking at their dissociation equations, and that, folks, is it. We will see you next time.